Hello everyone, welcome back to another discussion dynamics. In this discussion, we will talk about momentum of rigid bodies, and plan for today's discussion is brief lecture review and one example. So without further ado, let's dive straight into our discussion. Let me start with a brief lecture review. As you can see, I prepared something before our discussion. In here, I just draw momentum diagrams for a certain body experiencing such motion. So on this diagram, I showed state of the body at time instant t1. At this diagram, I showed state of the body at time instant t2. And in here, I showed what impulses act on our body between t1 and t2. Okay, so we know that our body has mass m and moment of inertia IC. That moment of inertia is about center of mass of our body. Our center of mass is located at point C, and we see that our body has some linear velocity vc1 and omega1 at the beginning. Additionally, there is a pin A that constrains our body. At time instant 2, we have vc2 and omega2, and between time instant t1 and t2, we have a couple of forces acting on our body. There is applied force F and applied force P, and there's also a moment rotating our body, moment M. And we also have a reaction force at pin A. Okay, so these are our momentum diagrams. Now let's turn them into momentum equations. So what happens in direction x? I think that in here I can write mvc1x plus integral from t1 to t2 is equal to, I believe, ax plus p dt. And this is equal to mvc2x. How about our momentum equation for the y direction? In here we will have vc1y plus integral from t1 to t2 of minus mg minus f and plus ay. Yes, these are all the forces acting in the y direction, dt. And this is equal to mvc2y. And now momentum equation, rotational momentum equation in the theta direction. So in here we have two choices. We can either write it about COM, and if we do that, it will look like that. So in here we will have IC omega1, but that omega rotates in a positive or negative fashion. It rotates in a negative fashion, so I should put minus in here. Plus integral from t1 to t2. And in here we have a couple of things rotating our body. First of all, we have a moment, and that moment again rotates in a negative fashion. So it will be minus m. And then what do we have rotating about point C? Force P is not rotating at all, but force F is rotating. And so we have F in here, F times L, and that rotates in a negative direction, so minus in front of it. And now we have AX and AY rotating. So we will have AX times H, and it rotates in a positive fashion, right? And AY as well, AY times L. Okay, so this is our rotational impulse, and this will be equal to IC omega 2. However, we have a pin in the system, point A is a pin. So we can also write our rotational equation about point A, because it's a pin. So in that case, we can start with IA omega 1 negative plus integral from T1 to T2 of, now I'm going to take moments about point A. So we will have mg in here. mgl, and it rotates in a positive fashion. We will have also mg rotates in a positive or negative? Negative fashion, right? Mg rotates in a negative fashion, sorry. No, positive, I'm sorry, I'm confused a little bit. Plus mgl. We have also moment m that rotates in a negative fashion, so it will be minus m. And also we will have force P rotating there. And it will be minus P times h dt. No other force is rotating about point A. And this will be equal to IA omega 2. Naturally, our IA is equal to IC plus MD squared, where D is this distance. D will be this distance. And this is a parallel axis theorem. Okay, so this is how we analyze momentum of our rigid bodies. We just to recap, we just start with drawing momentum diagrams where we show what happens with the body at the beginning and in the end. And we also show impulses acting on our body here. And then once we are done with our diagrams, then we are able to create momentum equations. In the x, in the y, and in the rotational direction. Oh, important thing. When it comes to the rotational momentum, you can go for either that direction or for that equation or for this equation, but never go for two of them simultaneously. If you go for this equation and this equation in your solution simultaneously, then you will end up with tautology. Your solution will be 0 equal to 0. So basically, you usually write momentum equation for x direction, for y direction, and then pick either this one or this one, but never two of them. Okay, with that brief lecture review, I think we can start solving our example number 1. This is example number 1, so feel free to pause the video and read and understand the problem statement before we start our solution. Okay, so what do we have in here? These are our knowns. We know that our sphere has mass m and radius r, and also the moment of inertia about its center of mass is 2 divided by 5 mr squared. Moreover, we know that V initial is V1 and omega initial is 0. And we also know mu k. And they ask us to find in part A, they ask us to find T2 such that our sphere rolls without slip. And in part B, they ask us to find v2 and omega 2 at time instant t2. Okay, so let's start our solution. Let's start with momentum diagrams. So I will show you what happens at time instant 0. I will also show you what happens at time instant t2. And in here I will show what happens between these two time instants. So we will have a sphere in here. This is its center of mass. And I can copy that sphere here and here. Okay, so our sphere definitely has mass and moment of inertia about point C. And our linear velocity is v1. And we have no rotation here. No rotation. In the end, we will have velocity v2 and some omega 2. And our sphere does not slip in here. No slip. And that means that our omega 2 will be equal to v2 divided by r. And now our impulses. What forces act on our system? We definitely have mg in here. We also have normal force. And let's say that we have friction also acting this direction. Let's not forget about our integral. So we will have to integrate this from 0 to t2 dt. Great. I think we are done with our momentum diagrams. We know what happens at the beginning, we know what happens in the end, and we know what happens in between these two time instants. Okay, time for momentum equations. I just would like to show what happens in the x direction, in the y direction, and in the theta direction. In the x direction, we will have initial momentum. We will have mv1 plus integral from 0 to t2 of minus tf dt, and this will be equal to mv2. In the y direction, at the beginning, we have 0 momentum. The impulse in that direction is following. We have n minus mg dt, and in the end, we again have 0 momentum. So that implies that our n will be equal to mg. N is equal to mg. How about theta direction? And I will write that equation about center of mass, so about point C. So at the beginning we have 0 rotation, so this will be 0. And then in here I will just show what forces rotate about point C. I think only TF is rotating, and it is rotating in a negative fashion. So it will be minus TF R dt. And in the end, we have IC omega 2, but positive or negative? It will be negative. So we will put minus in here. Okay, guys. So let's see what we have in here. I think we have 2 equations and 2 unknowns. But before we get there, we can also introduce our friction law, because in this system we have a kinetic friction. So Tf is equal to mu kn, and n is equal to mg, so it will be mu k mg. So we can now rewrite these two equations, because we will have mv1 minus 0 t2 mu k mg dt, and this is equal to mv2, and also from the third equation we will have minus integral from 0 to t2 mu k mgr dt, and this is equal to 2 divided by 5 mr squared omega 2, or actually in here I can write v2 divided by r, because we know that our omega 2 is v2 divided by r due to no slip condition. Okay, I would like to integrate, and I think that this integration will be pretty simple because our integrands are constant. This is constant, and also this is constant. So we can actually rewrite our equations in the following way. In here we will have mv1 minus mu k mg t2, and this is equal to mv2. And in the second equation we will have minus mu k mgr t2, and this is equal to 2 divided by 5 mr squared v2 divided by r. And I think I forgot about minus here. Yes, this minus. I forgot to put it here. There's a minus here. And there should be a minus here then. Okay, I think that there are a couple of things in our equations that can be simplified. So I think that we can get rid of m, and in the second equation as well. M cancels out with m, this r cancels out with this r, and this r cancels out with this r. So let's rewrite those equations one more time, this time in a simplified version. So in here we'll have v1 minus mu k g t2, and this is equal to v2. And in here we will have, oh, and that plus also can be simplified. I mean minus with minus, right? So in here we can have mu k g t2, 2 divided by 5 v2. Okay, and the easiest way to solve it is, so right now we just have two equations and two unknowns, because t2 is not known and also v2 is not known. And the easiest way to solve it is probably to add these two equations to each other. So let's add them, and we will end up with v1 equal to 7 divided by 5 v2, and that means that our v2 is equal to 5 divided by 7 v1, which was one of the things they asked us to find. And also that means that automatically our omega 2 is 5 divided by 7 v1 divided by r. So this is our answer B, these two expressions. Because we found v2 and omega 2, maybe let's express them in a vector form. So v2 will be 5 divided by 7 v1 0 0, and also omega 2 is 0 0 5 divided by 7 v1 divided by r. But I think it was clockwise, right? Let me scroll up the board. Yes, v2 was clockwise. So I should put minus in there. So it rotates in a clockwise direction. Okay. So now let's also solve part A, because in part A they ask us to find T2, I believe. Right? Yes, they ask us to find time needed to reach no slip condition. But I think it will be easy, because once we know V2, we can just use this expression to find T2. So let me take this expression. And from here you can see that our T2 is equal to 2 divided by 5. Actually, you know what, maybe before doing that, let's plug in V2 in here. Let's plug in our finding here. So this will be mu k g T2, and this is equal to 2 divided by 5, 5 divided by 7, V1. So this cancels out, and we end up with 2 divided by 7, V1. And that means that our T2 is equal to 2 divided by 7, V1 divided by mu k g. This is answer A. And I think that this is the end of the problem. Let me just double check if I have exactly the same answers in my notes. Yes, I have exactly the same answers in my notes. So yes, it looks like this is the end of the problem. So just keep in mind the procedure of solving these problems. I just would like to scroll up the board. In the momentum of rigid bodies problems, I usually start with momentum diagrams. And then, based on these diagrams, I create my momentum equations. And then, if needed, I just look for some more equations, for example, friction law, or maybe some kinematics. And after these 3 steps, I think that we should end up with exactly the same numbers of equations and exactly the same number of unknowns. That means that our system of equations is completed and can be solvable. So I think that I would like to stop here. I hope that you enjoyed that video. And in case you have any questions, just you can post them in the comment section below that video, or on Piazza, or you can visit us during our office hours. Thank you for your attention and have a nice weekend. Bye bye.